Hey guys, and welcome to Functional Print Friday. Let's get this dial indicator back together. So 2 weeks ago, we started on this thing, and if you missed that video, what's going on here is this is a dial indicator. This thing, as we push this goes around and tells us how far we've traveled. And this is a magnetic back for it. And this is not original to the indicator. I think what was going on was there was probably just a plain back on here. I'm guessing this piece was sold with this piece, and this is sort of like a universal fit for either a 3-hole or a 4-hole alignment here on this size dial indicator. It replaces the back, and then this screws onto this, and this is magnetic, so we can stick it onto a lathe bed or whatever we want, where this part stays stationary, and then there's some sort of travel here that we're measuring on the dial indicator. So unfortunately, this thing was never straight. Well, I don't know that. I mean, maybe it was straight at some point in its life. I doubt it. It looks to me like it's actually machined wrong. You see the significant slant there, the way it threads on. And it was off by quite a bit. I was thinking maybe this insert was just out of whack, like maybe it wasn't pressed in there straight, and I tried to push on it and I broke this part. So 2 weeks ago, we pulled this guy apart and I designed this part here, a replacement part for the back of the indicator, and all the screw holes line up. We're all good there. But you notice, big difference between these two items. This one has threads, this one does not. And my plan was to go ahead and try and machine the piece that presses into here on the lathe out of brass. I don't want to reuse this one because I think this one is actually the problem. I think it's this brass piece that's really the problem with this indicator back, because the brass piece on this one is flush with the back of this plate. That's correct, but it comes out of the plate at like a wonky angle. It's like they machined this part crooked. Anyway, I tried to make that piece last week. If you guys saw last week's like 45-second video of me saying, hey guys, sorry I screwed it up, no video this week, this is what I screwed up. I was almost all the way there. If you could take a look at this, what this should look like is a piece that presses into the back of this piece. And if you see here, you can see the problem. I cut way too much off, and it's such a shame because this was really the easiest part of the machining, was machining these two flats, a flat there and a flat on the other side to match these parts here. And I just, I did the math wrong. I was in a hurry. It was getting late. I wanted to get the video out. See if I can get a little bit closer, you guys can see that. I'm over by, I think what actually happened is I think I came over twice as far as I needed to. The problem is I didn't do a drawing for this. I just kind of winged it. I took all the measurements from the original one and from this piece as I was going, and that worked up until that last operation. So this week I have made myself an actual drawing of the piece that we're making. You'll notice I didn't bother drawing the threads in there, but I have, most importantly, I have all of the dimensions on here that I need. And in fact, the critical one here that I screwed up last time, you see I need to, there's a difference of 122 thousandths of an inch from our outside diameter here and where this flat should be. And I'm pretty sure that I was looking for 244 on the DRO on the milling machine when I screwed that up last week. So that makes sense. I think I just forgot to divide the number by 2. I think I remembered to divide the number by 2 from the center of the part, and then I don't know. I'm not sure. I screwed it up, but I have a drawing to work from this week. So let's get started. Now, I'm not going to try and talk while I do the lathe work. I might do some voiceover, but let me walk you through sort of in a real basic level what we're going to try and do first, so you understand what's going on. Because this is a 3D printing channel. I know most of you are probably not particularly interested in machining, but I do think that subtractive processes, which is really what you're doing on a lathe and a milling machine, you're starting with a solid piece of brass. Here's actually what's left over from making this piece. You're starting with a solid piece of material and you're taking off everything you don't need. Completely opposite to 3D printing, where you're starting with a spool of plastic, melting it, and just adding material on where you want. The thing is, not everything's a great fit for 3D printing, and I think this part is a perfect example of that. Could we have 3D printed these threads? Yeah, sure, we could have, but keep in mind, it's threading onto the back of this base, so we have that force when those threads reach the end and this tightens up, remember a thread is essentially like an inclined plane in a spiral. So there's quite a bit of force there. As we turn this onto here, it's just going to snap that at a layer line. There's no way it's going to hold up to regular everyday use, regardless of what filament we use. Yeah, if I gently put it on there, it's probably going to work. But now there's also going to be lateral force on this while we're using it. And then, you know, a month later, when I screw this thing on and I'm not thinking about it and I kind of make it a little bit tight and it just bloop, pops off, well, I'm either making a new one, or worst case scenario, the indicator drops on the floor as I'm threading it onto here, and now I'm out an indicator as well. So yes, subtractive processes, in this case using a mill and a lathe, sometimes are important. So let's go over to the lathe and I'll show you what we're going to do. Okay, so I'm not going to spend a lot of time talking about this. I'm going to give you just a really basic idea of what's going to happen here. So when you're seeing the video of this, you're understanding. On a lathe, which is what this is, your stock, or what you want to make something from, goes in this side. This is your chuck. This happens to be a 4-jaw chuck. I have this on here because we're going to use a collet block to hold our workpiece in so that we can take it out of here and then go over to the milling machine and mill those 2 flats on it when we're done. Also, it's going to enable us to machine half of this, flip it around, and hold the threaded part in the collet block in a collet chuck, which is not going to damage the threads, so that we can machine the other side. So again, our workpiece goes on this side. So what we're trying to make goes on this side. It spins around. Our cutting tool stays stationary on this side. And I have a set of hand wheels down here that I can use to control the position of that cutting tool. So if I turn this one, the cutting tool is going to move in that direction. And if I turn this one down here, the cutting tool is going to move back and forth in this direction. It's also a compound slide, but that's really not that particularly relevant to what we're going to do today. The other thing that's important to understand about how a lathe works is the movement of our spindle up here, which is what the chuck is attached to, and that's again where our workpiece is. The workpiece spins, tool stays stationary. When I spin this, notice that this is turning as well, and we can control how fast this turns in coordination with the spindle with these gear shift controls down here on the bottom of the front. That's important because that's how we make threads on a lathe. These two are mechanically tied together. This threaded piece down here and the rotation of this spindle. And how fast we turn this in relation to how fast we turn this allows us to cut different pitch threads. And we're going to actually cut the threads in the brass for this piece today with a threading tool. Right now, what's in here is just a standard cutting tool. This is going to enable us to turn the brass stock down to the size that we need. Once we get the outside diameter for the threaded section, I'll swap this in. And this is 30 degrees in both directions. And this is what's actually going to cut the threads. Here, actually, let me grab the other piece. Okay, here is our original part, the one that's broken, and here is the threading tool. And if I get close here, if we can get it to focus on this, you see what's going on here is this shape up here is what's actually going to cut these threads. The angle of this is the same as the angle of a standard thread. And if we're turning this part and this is moving this way, you see that it'll cut a spiral thread. So again, just some basic information about how a lathe works. This lathe, by the way, is a Precision Matthews PM 1440 GT. 1440 means it will swing a maximum of a 14-inch wide piece on this end, and it can be up to 40 inches long. The other tool that we're going to use is the milling machine. You guys have seen me use this on the channel before. This is a lot easier to understand, I think, how it works, because you could pretty much understand just by looking at it and touching the hand wheels. The spindle up here is where our tool bit goes. So in this case, the tool bit is spinning, much like other tools that you've probably seen and worked with. The workpiece stays stationary, gets mounted on the chuck down here, and I have 2 hand wheels. If I turn this hand wheel, the table moves in and out. If I turn either one of the hand wheels on the ends of the table moves back and forth. So you can imagine, once we've got our workpiece in here mounted up, everything else is done. For those 2 flats, we'll just mount it up in here. We'll get the correct distance away from the center point with the table in this direction, and then we'll move it back and forth in this direction to cut those flats. All right, let's get started. All right, and it is done, and I am super proud of this little piece. I think the surface finish on it looks pretty good, and all my dimensions on this, I either hit dead on or within 1,000th of an inch. I am by no means a professional machinist. I am really just learning how to use the lathe and the milling machine. But when you kick something out like this, even if it takes 2 tries to make it, it's just, you're super proud of it. It's just really satisfying to actually see it done. If anyone in the audience is actually a professional machinist, and you've got any tips for me from watching this video, please feel free to put them down in the comments. I will read them, but you know, at the end of the day, I got it done. I'm really happy with how this guy looks. And for comparison, here's the one that I screwed up last week, and you can see just how close I was to being done with this one before. I just simply, you know, just cut too much off making that first flat. So, all right, let's get this guy in place. All right, so here's our 3D printed part, and I think all that's really left to do is just go ahead and press this guy into place, which we can probably do with the arbor press. Might actually just pull into place if we thread this guy on and turn real hard, but I'm also a little bit worried about pulling this insert out of this base. I'm not sure how this goes together. I'm assuming that's one piece all the way through, but it's probably just pressure fit into this outer I guess hard plastic part. So we should probably just press this in. However, looking at this, I do think we can improve on the design of our 3D printed part a little bit. This is going to press in here, and I think it's going to stay in place, but I'm a little bit worried that in the future, if some pressure does get applied to this piece, either, you know, lining it up to push it to thread it in, or even just setting it down on a table, that it might push this part out. And I think we have room inside the indicator here. So this is the textured side is the side that's actually going to be out. This is the side that's going to be against the indicator. And it does sit in sort of this little stepped area here. But this triangle piece that ties everything together in here sits below this face. I'd say it sits below it by at least 1 millimeter. Now, I know we probably shouldn't count on that for another indicator, but at the end of the day, this indicator and this magnetic base are probably going to be pretty much married together, since I would have to unscrew this piece and screw it onto another indicator to use it with a different indicator anyway. So what I'm thinking is, I'm going to go make a quick modification to the design that raises up a ridge around this by just a little bit and then opens up on the inside. Not huge, like maybe, I mean, it might even only be like a 0.1 millimeter difference, but that this material is going to push through a section that's a little bit narrower and then drop into an opening that is a little bit wider, so that hopefully this guy stays seated in place even if there is a fair amount of pressure pushing from this side. All right, here we are. I think that came out pretty nice. It's even hard to really see the step in there, but we can see the portion that sticks up here. So let's first make sure this actually clears. Yeah, I can turn that all the way around in a circle here, and I'm not hitting any obstructions. So I think we are clear of everything inside. I did measure this. This was like 1.25 millimeters below this face, and I raised this section 1 millimeter. So we should still have some clearance in there. All right, I think it's time to really do it. Let's try and press this piece in. Okay, we're over here at the arbor press. You guys have seen me use this before. We turn this handle here. This moves up and down, and we've got a piece that we can spin around here to allow something to drop through. I'm a little worried though that if we use even the smallest one of these, that we're not going to distribute the weight very good across this plate. It's just going to bend. So I found a little plastic standoff. I think we're going to turn this around to a solid surface. Pop this guy underneath. We'll get this lined up as good as I can, and I'm hoping that this just drops in pretty easy without a ton of pressure. What I don't want to do is damage our brass piece. If this breaks because our clearances aren't quite enough, it's not the end of the world. I can print another one of these in like 20 minutes for 5 cents. The brass piece definitely took a little bit longer to make, and brass is not cheap. So let's see what we get here. I think we're in. Okay, we're in, but we're flush with the surface up here. I think it'll actually go in a little bit further. Let me find something that I can press with on the top, because this should actually drop through being flush and kind of click into place. So let me find something we can press on that with. Okay, I found another plastic standoff that is too big. Also found this little brass nut. That is not too big. That should work. Make sure we're centered. I do not want to push this thing off center. Okay, that dropped through no problem. Oh, dropped our standoff, but we're in. And you can see now we have dropped below this surface. And I can't push it back out. I do feel it moving a tiny bit in there. Yeah, it does move a little bit. So it does move between the bottom and sort of where our lip is at the top. I guess I could have designed those without as much gap. I was worried that this might chew into the plastic a little bit and eat up that clearance. But that's okay. As long as it doesn't back out, we're fine. And it doesn't. It just moves about 0.5 millimeter in there. Let's try it. All right, moment of truth. Okay, now it actually looks like it's going on crooked because we have that little bit of space up here that we can rock around on. But once it goes all the way on, it should straighten up. Yep, and it is dead straight. If you can see the slit of paper through there. All right, you know what, this is driving me nuts. I hate the fact that it can rock around on there. I think I'm going to go just adjust this quick so that the depth of the hole, or the size of the entire bore, matches the tighter section at the top to press through. I think that's going to give us a better all-around fit, and we should still have good retention just because it's going to be tough to push past those layer lines if the whole thing is snug. Let's see if I can get this out without damaging it. I'm going to be really sorry if I damage this brass piece. But this is, I can't leave stuff alone like this. It's just got to be as perfect as I can get it. Come on. Yeah, there we go. Okay, I'm going to go print another one of these that is a little bit snugger on the fit. Okay, while that's printing, there is something I want to talk about. So 2 weeks ago when we started this project, I also did just a quick recap on the East Coast RepRap Festival that I went to. And one of the things I talked about was the Peopoly printer that's coming out. Totally new drive system in that machine. It's a really cool looking printer. And in fact, it was the thumbnail of the video, and I said, this printer uses magnetic levitation. Well, several of you guys, got down in the comments and said, hey, I don't know what you're talking about. Do your research. It's not magnetic levitation. It's not Maglev. And to be honest, I don't know exactly how the printer works. There was a guy there that seemed somewhat knowledgeable about that printer. I didn't get an opportunity to speak to him. It's a really loud environment, and it's difficult to see just by looking at exactly how it works. But I didn't just make that up. Where I got that from was the marketing material that they were handing out at ERRP, the East Coast RepRap Festival. This is what I picked up in their booth at the show. And it says Maglev linear motor. And in fact, it says the same thing on this side as well, Maglev linear motor. Now, maybe that's just describing something with how the internal workings of the motor and not the actual rail system. I don't know. I don't know the details on how this machine works. I am potentially interested in getting one of these for two reasons. I think I mentioned in that video. Number one, it's just, it's something new. It's quite interesting, rather than using belts. And you guys also pointed out, I said it was Core XY. I caught myself actually when I was editing the video. I thought, it's not actually Core XY, because that refers to, positioning the tool head with the movement of multiple belts. That's not the case with this. It's just Cartesian. But when you watch it function, it works like you'd typically expect to see a modern Core XY belt-driven printer to operate. That's why I said that. I know it's not correct. I apologize. But I think a lot of people are going to think of it that way because it mimics the movements of a belt-driven Core XY printer. Anyway, let me know down in the comments if you guys know more from an engineering perspective of how this machine works. I've been on their website a bit. They don't go into a lot of details about exactly how it works. I'm not sure what they're specifically referring to when they say Maglev linear motor. And hey, maybe that's just marketing, not really understanding how the machine works, and they said that word and just went with it. I don't know, but it does definitely say Maglev linear motor on this. And in fact, on their website, at least at the time, I didn't go back and check today, it said Maglev 3D printer. So I'm not sure. This says Mag XY motion system. So maybe they're trying to figure out what to call it. Maybe Maglev or magnetic levitation is not really accurate, but they're trying to figure out what to call their motion system on a 3D printer. Let me know down in the comments if you guys would like to see this machine. I am, I don't think they're going to send me one for free. This channel's not big enough, but I am interested in this printer for a couple of reasons. Again, I mentioned the drive system on it is quite unique, whether it's magnetic levitation or not, or whether it's just some sort of, I don't know what they're exactly calling it. It does make sense that it wouldn't be magnetic levitation, because you would think that depending on where the tool head is positioned in the XY space, the drag is going to change from your Bowden tube or the filament tube coming down, which would knock this guy, you would think, out of it'd skew it if this thing was actually levitating. So there probably is some form of normal linear rail in there that I just can't see in the video and can't see in this picture. And again, I think the marketing department is just a little out of hand on calling this Maglev. But either way, I still think it's a cool design. But the other thing that draws me to this printer is the volume. I mean, it's 400 millimeters by 300 millimeters by 300 millimeters. That's a nice chunk bigger than the Bamboo Labs machines I have. In fact, it's a big enough machine that I'm not actually sure where I'd put it if I did get one. But I love the idea of being able to have that large of a print volume. Let me know down in the comments. What do you guys think? Is that big enough to go with for a larger format printer, or should I hold out for something bigger? Because that is the one printer that I want to add still to my stable, or whatever you want to call it, is a larger format machine. The Bamboo Labs is 256 by 256 by 256. Again, this is 400 by 300 by 300. Is that big enough? Should we wait for something else? Let me know what you think. Guys, as always, thanks for hanging out with me for this week's video. I know this turned into 3 weeks total to get this guy fixed, between designing the 3D printed part and machining that brass piece and screwing it up last week, but really happy I did this. Yeah, I could have just bought a new one of these, but I hate throwing stuff out, and give me an opportunity to not only sharpen my 3D printing and design skills, but also, kind of learn how to do a bit more on the lathe and the milling machine. And again, like I mentioned before, there's so much you can do with 3D printing, but sometimes there's just a part that just doesn't make sense to 3D print, and it's a better fit for subtractive manufacturing processes versus additive. If this is your first time on the channel, we do a new video like this, a new functional print every single week. If you're into that sort of thing, hit the like button. It's going to tell YouTube what type of stuff you like to watch. And if you really enjoyed this video, you like this channel, hit that subscribe button. Guys, if you do, I'll see you next Friday.